So yeah, so my title has two things, quantum integrability, and I forget if I said symmetric functions or symmetric polynomials, one of the two. I'll say polynomials because it's perhaps more precise. So today I'm really only going to talk about the first part, which is quantum integrability, because I suspect some of you are not maybe familiar with this subject. I suspect there is also a little bit of overlap maybe with some other lectures that you've heard, but still I think it's good to go back to basics. So the first probably two lectures will be about basics of quantum integrable systems. And then the next two lectures are going to be more about connections to combinatorics, and in particular to the theory of symmetric functions and symmetric polynomials. So what is quantum integrability? I'm not going to give you a full history of the subject. Again, I'm sure you must have heard some parts of this in other lectures, but it's a certain subject which happens to be mine. Which ranges from like physics to pure mathematics, and the history started with probably two seminal works. One was the work of Bethe. So this one we'll talk a little bit about because we'll talk about Bethe ansatz. So Bethe in 1931 solved a certain quantum system using a certain ansatz he invented for this purpose, and this kind of was remained an isolated story until much later, which is we're going to get to. So the other important event in this kind of prehistory of quantum integrable systems would be the exact solution of the Ising model, but I think you had a whole course on the Ising model, so I'm not going to talk about that much, but that was Onsager in 1944. So it's a very special integrable system, so in a sense, that story does not obviously generalize to what I want to talk about today. And the history of quantum integrable systems really begins in the 60s and 70s with people like Young, Lieb, and most importantly, Baxter in the 70s. These are people who investigated either quantum systems or models coming from statistical mechanics and produced some exact solutions using a bunch of tools, which we'll talk about in the next two lectures. And then finally comes sort of the golden age of integrable systems, which would be, in my opinion, the 80s, because these tools were refined, in particular the Leningrad school of Faddeev and his collaborators developed something called the quantum inverse scattering method, which is another name for algebraic Bethe ansatz, so some algebraic version of Bethe ansatz. So we'll do a little bit of that in the second lecture. Another important development in the 80s, which will not be covered in these lectures, is the connection to quantum groups. In fact, quantum groups were invented by Grünfeld and Jimbo precisely to sort of formalize certain algebraic structures behind integrable systems. So that's a very important direction, the connection to representation theory. I'll have a small word maybe tomorrow about that, but I know this is maybe not the main focus of these lectures, so we're not going to talk directly about quantum groups. And in recent years, there have been many new connections that have emerged between quantum integrable systems and various areas of physics and mathematics. My own interest is in connections to combinatorics, and that's going to be what these lectures are about. There's also very interesting connections to geometric representation theory, so algebraic geometry, which is also something I'm interested in, but we're not going to talk about that this week. All right, so this is the short historical discussion. So now let's actually begin. So first, what is a quantum integrable system? So well, the most naive answer comes from the name. It's the quantum analog. It's the quantum analog of a classical integrable system. Whatever quantum means and whatever classical integrable means. And that point of view is not the one I'm going to emphasize. So I'm kind of eliminating in these first few minutes everything I'm not going to do. So this point of view is not terribly useful for us because so there is definitely a notion of classical integrability in the sense of Liouville, which is you have this classical phase space and you have this family of Poisson commuting Hamiltonians, and you want to do some kind of quantum analog, but it's not so clear immediately why this is meaningful in a quantum mechanical world, because you can always find, when you have any operator acting on some Hilbert space, you can always find an infinite number of other operators that commute with it or something like that. So the formalism that is used in classical integrable systems is not obviously useful for our purposes. And what is more appropriate is this formalism I briefly mentioned of the quantum inverse scattering method, which, of course, itself is related to some further developments in classical integrable systems like the lax formalism. But we're not going to go through that route, in other words, because that's a complicated route, which is not appropriate for us. There is another version of it, which there's something called integrable quantum field theory. So you can make rigorous what the notion of an integrable quantum field theory is. So QFT means quantum field theory. There's something called factorized scattering. But again, quantum field theories are complicated objects, and we don't really want to do this today because, or in these lectures, because these are theories with an infinite number of degrees of freedom, which have all kinds of complications. So even though this is probably the only framework in which I can define rigorously what I mean by an integral quantum system, we're not going to talk about that. So the one I'm going to use today is a more pragmatic approach based on the Young-Baxter equation. So in the context of statistical mechanics, there is a well-defined notion of exactly solvable model, which is essentially the same thing as quantum integrable. Exactly solvable. And itself, that's related to something called the Young-Baxter equation, which we're definitely going to talk about today, which will be the main actor of today, in fact. So this is this third point of view we're going to talk about today. So, yeah, as I said, we're not going to talk so much about the more like algebraic aspects like quantum groups and stuff like that. So let's go straight into the story. Oh, by the way, I should probably also point out that there's a bunch of references. So actually, I don't know if Jules already made it. Let me just advertise, instead of giving you a bunch of references, they're really all pretty much contained in these. So Jules, who you know because he was already the assistant to the previous week, has actually written some pretty good introductions, a pretty good introduction to quantum integrability. And so the references, I suggest just looking at his. So this is the references for quantum integrable systems in his archive. So let's see if I can find it. 1501. So this is a general reference at a very low level, and so to speak. I mean, very pedagogical level to integrable systems. And did I get it right? Yeah, and so you can just look at the references there. He has a bunch of references, but anything I could say would be contained in what in his references. So yeah, these first two lectures are very classical material. There's plenty of references available on this. All right, so let's start with the basics. So you all know what statistical mechanics is about. I think this was pretty much the topic of all the other lectures anyway. So let's just introduce basic notations. For me, all we need to know is that there is a certain configuration space. So you have a set of configurations. Which I'll denote by C. And for me, because we're only really dealing with lattice models, this will always be a finite set. Of course, there are plenty of cases, of interested cases where this could be an infinite set, but I don't want to do that in these lectures. The next thing you have to have is an energy function, which is just a certain function E going from C to R union plus infinity. I'm allowing infinite energies because that's convenient. And then the basic tool is the fact that this automatically defines for you a certain probability measure on your configuration space, configurability measure. And that's the Gibbs law, which I'm sure has been, again, mentioned many times. Which is the fact that the probability of a particular configuration C, where C is in C, is given by the formula that it's proportional to the exponential minus beta times the energy of that state, where beta is a parameter, a real positive parameter, which is the inverse temperature. And Z is just a normalization constant, which is the partition function. So I think we can, oops. This is a good time for me to find the eraser. All right, partition function. Now, the partition function is not per se an object of interest because it's just a normalizing factor. However, you probably all know that even that, in fact, often all we care about is computing the partition function, even though it's not directly physically relevant. One of the ways you could argue, okay, so how does this work? I guess I'm gonna, that the partition function is useful is that if you know, so what we're really interested in computing normally is certain expectation values with respect to this probability measure. But the point is that even if you just know, even if one knows, for example, Z of beta for any beta, that already gives you some information. For example, you can compute the expectation value of the energy as being, like something like the d over d beta of log of Z, and I'm probably getting a minus sign somewhere. So, just to point out the fact that, even the partition function itself can be a useful thing to compute. And that's mostly what we're going to restrict to in what follows. There are more general observables, of course, which cannot be expressed directly in terms of the partition function, but mostly we're not going to do so much in these next few hours. And so the next thing we want to do is define lattice models. So lattice models means you have to have a certain underlying lattice, which can be, for example, in low dimensions, the obvious thing to do is to consider a graph. Oh, so E is already taken for energy, so, well, edges are kind of, okay, maybe I'm going to use some other font. So typically you have a graph made of vertices and edges. And then somehow the configuration space is defined in terms of these data on this graph. So before going into the model that is of direct interest to us today, I'm going to give a few examples. So for example, so these are all discrete models based on typically a graph. So given gamma, for example, you can define, I guess that was also something you learned last week. For example, if you talk about the Ising model, then the configuration space, C, is just maps from sigma from the vertices to plus or minus 1. And the energy of a configuration is just, sigma, I guess. E of sigma is just whatever it is. So maybe there's some coupling constant J, and then sum over. So yeah, let's say this is an undirected graph. Let's say we don't really. Later we may introduce orientations of the graph, but let's just say for now it's an undirected graph of whatever it is. Sigma is sigma J plus maybe some magnetic field, maybe, so some IV of sigma I. So something like that. Okay, so this is not actually what we're going to talk about today, the Ising model, if only because you've already heard of it last week. What I care about is so-called vertex models. These are the ones which are nicest from my point of view for various reasons. One of them being that the transfer matrix method applies most naturally to them. So I don't know how much you have heard of transfer matrices in the last week, but so this is what I want to talk about. So yes, so vertex models. So these are a special type of lattice model. And let me just say it in words, because there's not much point in formalizing too much all these simple concepts. Vertex models are the following. The degrees of freedom, so just in words, the degrees of freedom, as the name does not indicate, live on edges of the graph. But the energy function, and the energy function is a sum over energy, is a sum over vertices, basically. So it's the energy, each vertex has its kind of own energy. So this is the kind of models we want to talk about. And for kind of pedagogical purposes, I'm going to focus on one special case, which is important to me, which is this six-vertex model. So before we do that, so in principle, all that I've said so far could be, for any kind of graph, but we're mostly interested here in a kind of, well, square lattices or cubic lattices. So let me give an example of a graph. So in what follows, I guess, yeah, I might as well just say it now. In what follows, gamma will always be some region of the cubic lattice, let's say. And let me be specific. There are only really two cases of interest to us. The case where, and in fact, mostly square lattice, because very quickly we'll only work in 2 dimensions, which is the only dimensionality where this notion of quantum integrability is reasonable to define, let's just say. And so the first case is so-called periodic boundary conditions. So I'll put it in quotes, then I'll explain what I mean by that, though you probably already know, which is the case where V is just Z to the power D divided by some lattice, so some additive subgroup. Let's say for definiteness, let's even take it to be ZD divided by some product of. So basically just, and the edges are just nearest neighbors. And that's the obvious choice that we, and for D equals 2, that means it looks like something like this. So in this case, the 2 lengths are 4 and 3. And the point is that this is supposed to be periodic, so these actually are supposed to be, these 2 edges at the top and bottom are supposed to be identified, and similarly, these left and right edges are supposed to be identified. So this little symbol means that secretly these are supposed to be the same. All right, so you should think of it as just a regular square lattice, but living on a torus, basically, a d-dimensional torus, in this case, 2-dimensional torus. And so these are the vertices, these are the edges. So far, so good. So that's one case we're going to consider, and in fact, mostly we'll consider this one. There's the other case, which is I'll denote by fixed or open boundary conditions. And this is the case where you don't impose, so fixed, open boundary conditions. And that's the case where you have some domain. So we'll need it eventually a bit later. So that means in this case, V is some finite subset of Z to the power D. Again, E just being nearest neighbors. So for example, it could be just this. And by that, I mean that the vertices are these 4 vertices. In principle, you can also attach vertices to the endpoints here, but in some sense, we usually ignore those as being not so interesting. And so yeah, the typical example would be a sub-rectangular, like a rectangle inside a Z squared, for example. And fixed or open means it depends what happens at the boundary edges. You can either really count them in as being part of the system, and then the actual degree of freedom is allowed to fluctuate on these, or you may fix it in some way. So there's some choice of what happens at the boundary, and this is part of the data of the model. So as I said, probably in the second lecture, we'll need to actually do that. And in that case, I will explain precisely what happens at the boundaries. But probably the simplest example to have in mind are these periodic boundary conditions, because they're the most natural, they're the ones that have the most symmetry in some sense. All right, so now we get to the main topic today, which is this six-vertex model, which is a particular vertex model, as the name indicates. It's the prototype of the integrable quantum integrable system, or if you prefer, exactly solvable lattice model. The way that it works, so the first I have to define to you, so this is all in 2 dimensions, so d equals 2. In principle, you can define it in a more general setting for more general graphs and so on, but again, for simplicity, we'll restrict to exactly this kind of, the square lattice. And the first thing I have to define for you is what is the state of configurations. Well, in this case, it almost looks very similar in some sense to the Ising model, except as I said, the degrees of freedom live on edges. So it's more like sigma goes from E to, let's say, plus or minus 1. So in other words, each edge can have 2 states, which can be described by either plus and minus or a variety of other ways. In fact, I prefer, well, yeah, okay. So let's do a small example. I don't know, so maybe plus, plus, minus, minus, and probably something here as well. Plus, okay. I'm going to have an example which is vaguely reasonable, so plus, minus, whatever, plus, minus, plus something. Oh, no, so, yeah, okay, yeah. So each edge has either a plus or minus, but this is not a very particularly illuminating picture, so there's actually a better way to think about it, which is, so there are other alternative descriptions of the configuration space, alternative descriptions, and the one that's probably most illuminating is the one in terms of arrows. So the way it goes is as follows. You fix an overall orientation of the picture. Let's say if your lines are going like horizontal and vertical, you fix kind of a direction of, overall direction of the flow, which is, say, everything is going northeast. And then you declare that if a plus, if you have a plus, then you put instead of, you replace it with an arrow in the direction of the flow, so either, well, in this case, either up or right. Or if you have a minus, you replace it with an arrow which is kind of opposed to the flow. That means it's going either down or left. So this is it's not particularly convenient for practical purposes, but it does kind of show a little bit more what we're doing. In this case, so plus would be going this way. I don't know, so down. Minus goes against, plus, minus, plus, minus. All right. The reason this picture is a little bit nicer, at least one of the reasons, is that you see naturally when you look now at any, so eventually we'll have to define an energy function at every vertex. And there's a very natural condition you can impose on configurations, which is that when you have arrows which are around the vertex, you may count the number of incoming arrows and the number of outgoing arrows. And a configuration is set to satisfy the ice rule. Configuration, whatever, sigma satisfies the ice rule. That's just by definition. If and only if the number of incoming arrows at a given vertex v in V is equal to the number of outgoing arrows. So, of course, you could also express it in terms of pluses and minuses, but it's a little bit at V for all V. The reason we care about this ice rule, okay, the name ice rule I'll explain in a few minutes, but first, the reason we care about it, we only want to consider, an energy function E such that the energy basically is finite if and only if, Yes, if and only if, such that, so E is finite, or if you prefer the corresponding energy, sigma is finite, which is the same as saying that the probability is non-zero of that state, if and only if sigma satisfies the ice rule. Right, so we only want to really consider configurations which do satisfy the ice rule. Everybody else is going to contribute, will have zero probability. Why we do this? Well, just a nice property to ask for. Right. Oops. So let's have a look at, before we go on with alternative interpretations, so alternative descriptions, let's see what this means, this ice rule in practice for a vertex. So in practice, at a given vertex, what are the possibilities of arrows? So every vertex is just a 4-valent vertex. It has 4 edges. What are the possibilities of arrows going in, going out? Since there are 4 edges, 2 of them must be incoming, 2 of them must be outgoing. So that's 4 choose 2 possibilities, which is 6 possibilities, right? And hence the name six-vertex model. 6 possibilities, yes. So either they go all, so there are 4 possibilities where the arrows are kind of, so right, right, left, left. Yeah, I probably shouldn't have drawn this way, of course. No. Yeah, let me put these 2 under. And finally, there are 2 other possibilities, which are where the arrows are kind of pointing at each other horizontally or vertically. All right, so 6 possibilities. The other thing we want to do is we're going to impose, there's another natural symmetry which is apparent in this arrow picture, is the parity, or arrow, which is the same as arrow reversal. So that means when you have a configuration, you can associate a new configuration, arrow reversal. So when you have configuration sigma, you can associate a new sigma bar where all arrows are reversed. Of course, in terms of signs, that's just replacing sigma with minus sigma if you prefer. So maybe, yeah, I could denote it minus sigma, but anyway. So in particular, you note that in terms of vertices, that means I've intentionally drawn them in such a way that if you reverse all the arrows, locally, these 2 configurations are exchanged and these 2 are exchanged, and so on. So there are 6 local configurations, but they come in pairs, which are related to each other by reversal of the arrows. And we also want to have an energy function that's invariant under that parity. So we want E of sigma equals of E of sigma bar. Right? So now if you put all these things together and the assumption that the energy is just a sum of configurations, sum of local energies depending only on the edges around a given vertex, you see that you don't really have so many possibilities. So that means at the end of the day, the energy of a configuration is the sum over all the vertices of something that depends only on how the vertex looks like. That means, you know, every vertex has to be one of these 6 types. And since these 2 are related by spin reversal, that means they should also have the same energy. So let's call epsilon A the energy of this one, epsilon B of this one, epsilon C of this one. That means it's a sum over all vertices of epsilon A, epsilon B, epsilon C, depending on the edges around V. So that defines and so all of these energies are just real numbers, right? So all of these are, say, real numbers. All right, in practice, as is often the case, we don't really care so much about the energy. We care only about the actual probability, which means we only care about the exponentials of minus beta times the energy. So it's convenient to redefine A to be exponential minus beta epsilon A, B to be exponential minus beta epsilon B, C to be exponential minus beta epsilon C. And if you don't really care about the dependence on temperature, then these are all the parameters you care about. So the model is really defined in terms of these three parameters, and these are just positive real numbers. All right, so that's the definition of the six-vertex model in a nutshell. In principle, you could relax some of these conditions. You could ask maybe for energies which break the parity and things like that. But you know, it's really the simplest setting in which we can say something interesting. All right. Next. So yeah, I guess I have to erase now. So there's a couple more ways, before we go on with analyzing this model, there's a couple more ways you can think about describing the system, describing the configurations. And in particular, one of them has to do with this name ice rule. Yeah, all right. So this is the so-called square ice. So in other words, one of the reasons you could consider introducing this model has actually to do with something to do with ice in the sense of, yes? Yeah. Absolutely. Right. So if you impose rotational symmetry, then A should be equal to B. And that's perfectly fine. That's, in fact, an interesting special case. But really, it doesn't make the solution easier or harder. So we're not going to impose it. But you're absolutely right. Yes. A equals B is an interesting special case. There's an even more special case where all A and B and C are all equal. And that's like the infinite temperature limit where, you know, every Boltzmann weight is equal to 1, so every configuration is equiprobable. And we'll talk about that on Wednesday, I guess. Okay, so yeah, one quick sort of historical word on why. Yeah, why the word ice and the ice rule? Well, this is as follows. There's yet another way you can present the same model, which is imagine a lattice, square lattice made of oxygen. So made of oxygen, whatever, atoms or something. Okay, my physics background is, I'm forgetting the fact that it used to be that I actually knew some physics, but that was a long time ago. Anyway, so you have oxygen atoms on a regular square lattice. And so you imagine this is square ice. It's two-dimensional ice. So you only have like one single layer of atoms. These are your oxygens. And the question is where do the hydrogen ions or atoms or whatever. So you know that should be, you know, like, so it should be something like H2O. That means every oxygen should have two hydrogens nearby. And the way you indicate that is by saying that, so the assumption is that the hydrogens actually live on the edges of the square lattice now. And so potentially, okay, no, I'm putting too many for, okay. So the way it goes is that you're saying, okay, so this hydrogen maybe is connected to this one, maybe this hydrogen is connected to this one. And so the point is that, okay, so maybe this one's connected to this one. Okay, maybe I should erase those little. So the way it goes is that eventually you find that effectively you get arrows on every edge of your square lattice. And because, you know, every oxygen has to have two hydrogens, that means you should have two incoming arrows at each vertex, which is exactly that ice rule. So that, hence the name ice rule. And so in principle, you can think of this as a sort of very schematic model for square ice. In particular, you can try to compute the residual entropy. using these methods of integrable systems that we're going to talk about. So there's a kind of a vague physical motivation for why this is interesting. All right, so the next thing we want to do is discuss a little bit how to compute the partition function. Oh, right. So in principle, what do we want to do? We could compute the partition function. That's the first thing we could do. So just the sum over all configurations of of this. So sum over all sigma of exponential minus beta e of sigma, which in practice involves only these three parameters a, b, c. So it's a certain big polynomial in a, b, c. Or we could compute, in principle, correlation functions. So in vertex models, the easiest correlations would be you pick your favorite function on each edge, and you just try to compute its expectation value. So for example, in this case, correlation functions could be something like I don't know. So you pick edges, E1, En, and you just try to compute the expectation value of sigma E1, sigma En, where the expectation is over that probability measure, given by Gibbs law. Yeah, that's a typical objective. So how are we going to do this? That's the next stage. We're going to do it. I wish I could find my notes. That would really help. Just a second. Okay, technology is not helping me today. Just a second. Okay, this is not working. All right, no big deal. Okay, so what we're going to do, so I was in the process of erasing. Which part should be erased? Probably here. So yeah, in what follows, let's say we try to compute the partition function as a starting point. So how do you do this? So the key tool we're going to use, and that will be the subject of probably the remaining probably half hour, however long we have, is transfer matrices. Maybe I should say one more word. So yeah, so compute the partition function, and perhaps, so I should point out the obvious fact that the partition function still depends on the actual lattice. So remember, we had those doubly periodic conditions. Let's say we consider the partition function with periodic boundary conditions. And that means our vertex set would be something like, in this case, let's say z over, kz times z over lz. Because this is in 2 dimensions. So we just doubly periodic with sizes in, say, this may be the vertical direction, the height of the system, and L would be the width of the system or something like that. So really, that means Z is actually a function of K and L. And in actual statistical mechanics, again, maybe very quickly we'll not really do any kind of physics, but in actual statistical mechanics, what you're supposed to do is consider systems with a very large number of degrees of freedom, which means really, normally at the end of the day, you're supposed to, send K and L to infinity and look at what happens. And, in particular, one thing you may want to compute is the what's called the free energy, the bulk free energy, which is the would-be limit. So let me put a question mark here. Limit when KL goes to infinity of log of Z over K times L. So the idea is that the log of the energy, the log of the partition function, this is the free energy, should be somehow extensive. That means it should grow like the surface of your lattice, which is K times L. So there's of course a question. There are several questions there. First, what do I mean exactly by the limit k goes to infinity? There are several ways you can take limit. You can take limit k goes to infinity first, or L goes to infinity first, or you could try to maybe to combine them, take some mixed limit. So it's not clear that, that limit makes any sense. Now, there are general theorems of statistical mechanics that tell you that for any spin model or any vertex model in which all energy, so maybe this is a small side remark before we proceed, if the energy function E of any configuration C is less than infinity for all C, then in a very general class of, well, for essentially any vertex models or any spin models, it is known that such a limit exists, known that limit KL goes to infinity, say of log of Z divided by KL exists and is independent of the order and is independent of the order of the limits. In fact, there's much stronger statements than that. It also typically doesn't depend on the boundary conditions. That means you can change periodic free boundary conditions. You'll always get the same result in the limit. So this is a very weak version of a fairly strong statement, which is that essentially that's the existence of the thermodynamic limit in the usual statistical mechanical jargon. However, you have to be careful that this does not apply to the six-vertex model. Doesn't apply to the six-vertex model. Why? Because remember that we imposed the condition that somewhere. Yes. We imposed the condition that only configurations that satisfy the ice rule have finite energy. All other configurations have zero Boltzmann-White, that means infinite energy. So by doing that, of course, we're strongly constraining the system, and that prevents the usual theorems of statistical mechanics from applying. And in fact, it is a fairly, by now, well-known phenomenon that indeed the thermodynamic limit in the usual sense does not exist for the six-vertex model. And yeah, so we'll get back to that eventually. All right, so the next thing I want to talk about is transfer matrices. So we're trying to compute Z, partition function. And the way we're going to do it, first we'll introduce a bit of graphical calculus, and then we'll express it in terms of kind of linear algebra. We'll express it in terms of basically a big matrix or a linear operator called the transfer matrix. Okay, so let's first talk about graphical calculus. So this is just a convenient way of representing expressions using only pictures, basically, which is something I really like. And so the basic idea is that, well, it's basically a rule where when you draw a graph, what we really mean by the graph is the corresponding partition function. So this is what I kind of, in a nutshell, is like draw a graph equals compute its partition function, basically. So let me explain what I mean by that. So let's take an arbitrary subgraph so pick an arbitrary subgraph of say, the square lattice. And so that's the part, yes, a bit like in this story, like fixed boundary conditions. That means you take some region, so for example, this subgraph, and you do the following. You declare that, so the first thing to notice, I promised I would say more about that, is that there are two types of edges. There are external edges and internal edges. So the external ones would be, these. So maybe I'll, the external ones would be like these in this case. And the internal edges are all the other ones. And once you've done that, you say that when you write such a picture, what you really mean is that okay, so then you should label external edges, always, as a rule, using actual configurations. using, in the case of our six-vertex models, that means using plus or minus or arrows or whichever, or hydrogen bonds, or whatever you want to use. So in this case, that means you fix, let's say we use the arrow notation, we fix the arrows on all the external edges. Okay, let's see if I can make something that's vaguely, yeah, that works. Okay, and then such a picture, by definition, you say that it's equal to, okay, so the rule is that all the internal edges are free to be whatever they are. So that means this thing is, by definition, the sum over all possibilities, all choices of internal edges, labels of the corresponding Boltzmann weight. Right? So that means in practice, in this case, for example, when I draw such a picture, what I really mean is this is the sum of, it's the Boltzmann weight of all the possibilities. Well, the sum of Boltzmann weights of all the possibilities of putting something inside. So there are not so many possibilities. I think I chose an example where there are only two. So in this case, let me quickly redraw it. So, like this. So in this case, either you have this one, or you have the other one. Hopefully, I got it right. No, I completely screwed it up. No, this is not right. There are three incoming here. Oops, let me try again. Let's try again. No, so yeah, that's kind of stupid. There's only one configuration, fine. Okay, that's a terrible example. Anyway, how about we change the example to make it less stupid? Yeah, some error went the wrong way at some point. Yeah, let's change it. All right, let's try again. That's probably better. All right, and so now what I was doing earlier was correct. Either it goes this way or it goes that way. And that means in this case, it's, you have a vertex here of type A, a vertex of type B, a vertex of type B again. And okay, this is not so exciting, but anyway, so this is A squared, B squared. And this one is a vertex of type C. This is all C's, I guess, so plus C4. Right? So it's just a, this is the way we think about when we draw a picture, it's what we mean. What else did I want to say before we go on and actually introduce transfer matrices? Oh, sorry. Well, correct, in which case the answer is 0. You're right. In fact, yeah, that's absolutely right. So it's the sum over all allowed configurations. Yeah, because of the fact that the model has this restriction, which is the ice rule, in fact, there's a very easy necessary condition for the result to be non-zero, is that there's as many incoming and outgoing edges, around the, so that's not what I failed in my case, but yeah, I mean, it's a necessary condition, let's just say. So here I carefully chose so that there are as many incoming and outgoing arrows, around the, like on the boundary, so that there's a chance of it being non-zero. But you're right, in principle, the answer could be just 0. Yes. In fact, it'll be 0, as I said, in many cases, as soon as you're violating the ice rule, as soon as you have more, for example, incoming arrows than outgoing arrows. Right, so before we proceed, I realize I forgot to give one more, okay, but maybe that can be, yeah, I wanted to do one more alternative description, which I forgot, which is the one in terms of path. So none of these descriptions are particularly convenient when it comes to actually playing, doing actual calculations, so I want to introduce one more description in terms of paths, so maybe I'll just insert it randomly here because it's not going to take us very long. So the path description. So what we're going to do is this time we're going to say a plus. So I think with my convention, I'm going to draw it as being a, okay, so what's going to be my graphical convention? I guess I'm going to use blue colors. So I'm going to use it to say it's a occupied state of my edge. So in other words, I'm going to use a dictionary. I'm going to say that plus is occupied and minus is empty. And I'm going to draw this just for the, maybe, I don't know, I'm going to use dotted lines maybe to say empty. So the way I want to think about it is, yeah, so some edges are occupied, some are empty, basically. It's just a more convenient way to actually draw the pictures. So in the example above, that means let's do it, so you start with the same graph, and then you say this was occupied, 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 and then this is occupied, occupied. So it's just prettier, basically. And also, it's kind of natural what the ICE rule means in this language, though you have to be a little bit careful. What it says is that, so the ICE rule in the language of path says first thing, obviously, that paths are continuous, but it says more than that. It says, so the ICE rule in this language, so this is a smaller remark, it says that at every vertex, there should be an incoming path from either the left or the bottom. So at every vertex, there is a path arriving from either south or west, and leaving from, no, that's not true. Wait, what did I mean? No, that's not true. I got it wrong. The path. No, but there's also the empty configuration and the full configuration. Right. Right. So yeah. So it's no. I mean, I phrased it badly, basically, because this way it seems to indicate that there is always a path going through every vertex, which is not correct. So how to formulate it better? Yeah, every vertex path. Okay, maybe I should. Path arrive. Yeah, sure. Yes, yes. Path arrive from south or west and leave from north or east. But there's definitely the possibility that there's zero path or one path or two path. I guess my example had none of these. Yeah, right. All right. Next, the notion of transfer matrix. So the transfer matrix in this language is just a way of subdividing, you know, it's like divide and conquer. You're going to divide your lattice into smaller bits, and then you hope that the partition function can be expressed in terms of these smaller bits. So in this language, the transfer matrix, which generically will denote by the letter T, is the following object. First, it's a matrix. Then we'll, of course, think about it as a linear operator, but very explicitly, it's a matrix. So you fix sigma 1 dot 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 sigma L, and then sigma prime 1, sigma prime L to be plus or minus, or again, any equivalent formulation, empty occupied, whichever language you prefer. And then you say that T sigma 1 dot 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 sigma L, sigma prime 1, sigma prime L is equals to this thing. There are else sites here. So you can think of it as just being one row of that picture. And to conform with my convention that I should always fix the edges, every external edges. On this picture, all of these vertical edges are external. That means I have to fix them. And I fix them, obviously, by saying that this is sigma 1, this is sigma L, sigma prime 2, sigma prime L, right? And again, by that picture, what I mean is that you should really sum over all the internal edges, which in this case are all the horizontal edges. So secretly, that means sum over all horizontal edges, being themselves either plus minus of the corresponding Boltzmann weight. Which is this product of A, B, C in practice. All right, so why is this useful? First, before we even discuss it's the sort of linear algebraic meaning, first, why is this a natural thing to do? Well, it's natural because you can think, clearly, if you're going to stack together many of these pictures together, you're going to get the full lattice. So that's the joy of this graphical calculus. You can literally do that. You can kind of glue things together. So let's first do it, as I said, in the pedestrian way, and then we'll do it in more like linear algebraic way. So if you now have a full lattice, let's say for starters a 2-row lattice, let's say in this language if k equals 2, we could do k equals 1, but that'd be really boring. And you're trying to compute the partition function, which is supposed to be, again, in this abstract language, is literally equal to that thing. And here you notice there are no external edges. So the implicit convention is I'm summing over all edges, which is what we were supposed to do for the partition function. Well, it's very tempting to try to cut it by saying, how about I rewrite this way? So I take my pair of scissors and I cut all the vertical edges. But of course, now they've become external edges. That means I have to fix them. And I say, well, fair enough. It's the sum over all values here, sigma 1, sigma 2, dot, 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 sigma L. But here, of course, it's the same value, because when we cut the edges, these were really the same edges. So it's also sigma 1 here, sigma 2 here, sigma L. And similarly, here you're supposed to sum over all the values of these vertical edges, but now they're external, so I actually have to specify them explicitly. So I get that formally these two expressions are the same. And again, I'm still missing sigma prime 1 on top. And again, the convention is that there's implicit summation over the horizontal edges. It's still there, but we're not writing it. And so explicitly, that means it's nothing but sum over sigma 1, sigma L, sigma prime 1, sigma prime L of T. Let me just write it T sigma prime, sigma T, sigma, sigma prime by using kind of a slightly condensed notation for all the sigma 1s, sigma L being a single symbol, sigma prime. Right. And clearly, this reasoning can generalize to any number of rows, right? In general, you'll find that for any k, you'll find a rather cumbersome expression, but which is pretty obvious. You're going to get a summation over, sigma 1, which is itself, which is sigma 1, dot, 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 sigma 1, L, and then dot, 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 sigma k, which is sigma k1. So you're going to have a bunch of intermediate configurations corresponding to the various places where you cut. And then you just get a product of something like T sigma I plus 1, summation from I equals 1 to k, with the implicit convention that k plus 1 is the same as 1. So we're working mod. Remember, we're working in z over kz. So we're working mod k. So the basic idea is that, the partition function is just really a product of k transform matrices, of these mysterious t's, corresponding to the fact that the whole lattice is just basically the concatenation of k rows. It's a pretty obvious statement. And the linear sort of algebra interpretation is pretty obvious as well. We're just going to think of this as an actual matrix, or if you prefer, we're going to introduce a vector space on which it acts and think of it as a linear operator. So let's do that. So let C2 be equipped with its standard basis, which equipped with a standard basis. So which I'm going to, so in other words, the pluses and minuses, I'm going to think of them as being basically basis vectors. So I'm going to use this kind of physics notation of Ketz. So I'm going to say plus is 1, 0, and minus is 0, 1, basically. So just, whatever notation you want to use for the two standard basis vectors. And I'm going to now define a linear operator by saying that this is the linear operator whose matrix elements are this thing. So that means now let T be an element of endomorphism of what? So I want to think of, I'm going to add now some extra information, which is I want to think of the sigmas at the bottom as being the input and the sigma prime at the top as being the output. So at this stage, I make an implicit choice, which is some kind of direction of time. The time flows for me upwards. This is the input, this is the output. Like if you're doing programming, you have those little diagrams where, the input comes in, there's a black box, and then the output comes out. So T is going to be my black box, but I want to think of the sigmas being the input. That means the vector space on which T is going to act has to be labeled by sequences of spins of L, L plus or minuses. So so if you just take C2, that's just 1 plus or minus. So what I need to do is to take C2 and tensor it L times. So again, now the basis of C2 tensor L has a basis which is given simply by tensor product I equals 1 to L of basically just sigma I. So I should always think of it as in this canonical basis, which is just tensor product of either 1, 0 or 0, 1, where sigma I lives in plus or minus to the power L. Right, so in this basis, and then the claim is that T, by definition, be given by the fact that its matrix is this thing. That means T acting on, well, exactly what I wrote here. I guess I'll rewrite it again. Product of 1 to L of sigma I. Sorry, right, sigma n, right. Is equal to sum, sum over sigma prime 1, sigma prime L of T sigma prime 1 dot dot sigma prime L, sigma 1, sigma L, and here just the tensor product of it. Right, so there's just the obvious thing. This is the linear operator that kind of implements the following transformation. Given the bottom, it gives you what the top, it gives you a linear combination of all the possibilities for the top, where the coefficient is whatever Boltzmann weight is attached to it, right? So it kind of gives you, it's a very natural way of translating this kind of statistical mechanics problem into more like really a quantum mechanical system in which you have a time evolution. You're starting from one row, and somehow you're evolving it into the next row. This is also, by the way, a very practical way of thinking about, if you actually want to compute with a computer the partition function of a statistical mechanical model, using a transform matrix approach is actually usually a very efficient numerical method to do it, because you literally want to do it this way. You don't want to sum over each, the summation over all the spins is a huge sum if the system becomes huge, so it becomes large. So whereas the transform matrix is only kind of large in one direction, so you've kind of gained one dimension in some sense by doing this operation. Anyway, this is just philosophy. Now let's get back to our business. The interesting thing is each time you have now summations over intermediate states. This is just like taking products of operators. So here the morale is that vertical concatenation of diagrams of pictures or whatever I call them, graphical. Yeah, let's say of diagrams, is like multiplying linear operators. So that means in practice, for example, this summation here, in fact, yeah, well, we might as well do it directly the general case. Each time we're summing, we're, okay, yeah, let me write it. So that means explicitly, that means if you're doing sum over sigma prime of t sigma, sigma prime, where again, I'm using this slightly condensed notation that each sigma is a collection of indices, sigma prime, sigma second. So this is always, in plus or minus to the power L. This thing, you should just think of it as just being t squared sigma sigma second for all sigma second, again, in plus or minus L. Right? So the idea is simply that all this concatenation is just taking products of this transmatrix viewed as an operator acting on this big tensor product of copies of C2. So at the end of the day, if you look at this general expression, we have k summations. Each of them, it's like a cyclic thing. So really what you do is you're taking the kth power of t because you're concatenating k rows together. But since we're now imposing cyclic boundary conditions, periodic boundary conditions vertically as well, that means you're taking the trace. So if you've never seen this before, it might take a while to sink in, but if you've already seen this, it's kind of almost obvious. Again, all I'm saying is the fact that what I've done is I started from my partition function with doubly periodic boundary conditions. I sliced it vertically, and then I said that really, when I glue things back together, all I'm doing is taking the product, and the cyclicity of the trace ensures that you have periodicity of boundary conditions, basically. So we reached the really important conclusion that we can express the partition function as simply the trace of a certain linear operator. And now the question is what to do with this linear operator. So this is the transfer matrix approach. All right. So ideally, yeah, so before we proceed, let me say something completely general. So first, everything I said, in fact, is completely general. Any vertex model can be analyzed in exactly the same way, and you will get the exact same result that, for example, the partition function on the torus will always be equal to the trace of the kth power of some transfer matrix. This is even true in any dimension. You always have to just kind of isolate one dimension, which is kind of like this discrete time in which you're evolving, and then define the transfer matrix as being one slice, one dimension lower. So it's a completely general tool. It also would work for spin models, but it's a bit trickier for spin models, like for the Ising model, for example. So it's much nicer here in this vertex model setting. The other completely general thing I can say is that once you've expressed Z as the trace of t to the power L, T is an endomorphism. That means it has eigenvalues. This is all in finite dimensions. It's a finite dimensional, an endomorphism of a finite dimensional space. That means you know that it can be expressed as the sum 1 to whatever the dimension of your space is, 2 to the Lth of the lambda I to the power L. Well, lambda i's are the eigenvalues, if you like, of T. If it's not diagonalizable, it's not a big deal. You just, you can still do it. This is true in complete generality. So that means, in principle, all you need to do now is just compute the spectrum of this transfer matrix T. So that's what we're going to do. In particular, as L goes to infinity, this is dominated. Let's assume that let's assume that lambda 1 is an eigenvalue which is greater than lambda 2 and so on. Let's assume that the spectrum is, just to simplify, that there's no, the spectrum is in such a way that there's a unique eigenvalue with a maximal modulus, which is true in many circumstances thanks to this Fermat-Frobenius theorem. So in many cases, this is literally true. Then you find that the most important contribution as L goes to infinity is the largest eigenvalue. So really, if you're really only interested in L goes to infinity, you don't need to compute every eigenvalue. You need to compute one eigenvalue. So that doesn't seem too bad. OK, so how would we go about doing that? The first thing we're going to do, so this is completely general, what I said. But in fact, what I'm going to say next is also general, but it's really only very useful if you do it for integrable systems. So we're going to proceed further and introduce so-called R matrices. So R matrices is just, you iterate this process once more, basically. It sounds pretty stupid, but, this is what we need to do. So what we're going to do now is we're going to say, well, we divided the partition function into, vertical slices. How about we just do the same, but with the transfer matrix? So we slice it again, but this time horizontally, right? So that's kind of the next obvious thing to do. So slice again. So we say the transfer matrix was this thing. But of course, we can do the slicing in the other direction. And so we can write it as sum over, whatever, row 1, row L of these things. Row 1, row 2, sigma 1, sigma prime 1. And by now, it's become a complete tautology. Obviously, this is just literally decomposing all the way to into individual vertices, basically. Dot, dot, dot. And then the final one would be row L, row 1, sigma prime L, sigma L. Right? So I divide it even further. This is kind of a tautology, but the point is that, again, you can think of this as a big product of matrices. And the matrices now, so the R matrix are just the matrices corresponding to a single vertex, basically. So, so we're going to play the same game. And we're going to define the R matrix R to be an endomorphism, this time over a single copy of C2. So this time, you should think of it as follows. You have two lines coming in. So the kind of flow of time now is going, let's say, this way. So you have two inputs and two outputs. So this is the input. Let's say there's some conventional choice to be made. This is the output. And so what it says is that so let's do a little picture of all the possibilities. So maybe for a change, oh yeah, I'm going to use this path notation that I haven't used so much yet. It's pluses and minuses. So I think I used blue colors to draw the path. Sorry, L. Oops. L matrices. R is kind of the same as L, right? So yeah, sorry. Yeah, sorry. They're called L matrices. You'll see later that they also call R matrices. But yeah, sorry. Yeah. And so the rule is that when you write a matrix, the input is like the index of the column of the matrix, and the yes. Right. No. So I think they're still periodic because I put a row 1 here and a row 1 here. So it's still kind of. All right. Yeah. Okay. Sorry. Right. We're getting there by successive approximation. Sorry. There are two inputs and two outputs, so it's C2 times C2. Thank you. So it's a 4x4 matrix. And so all the possible inputs are, so what is it? Occupied, 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 empty, empty, occupied, and empty, empty. And the vertex being here. Really? Blue is no good? Okay, well, we have to change then. Now the paths are in red. And similarly, the output can be either occupied, occupied, or okay, so we have to be careful. There are conventional choices of which one is, yeah. That's an important and annoying technicality that needs to be discussed. When you're taking tensor products, there's an implicit choice which is of the ordering of, which one do you consider first, which one you consider second. So in the L matrix, the convention is always we're going to read this as being sigma 1 here, sigma 2 here, and strangely enough, this is going to be sigma prime 1, sigma prime 2. That means the reason is we kind of want to, preserve the horizontality of verticality. It's not a very important point, but I want to think about it this way. So what it means in practice is that it only matters for the just ordering of the rows and columns of this matrix if you write it explicitly. So that's the choice I'm going to make here. So that means I do not change the horizontal one. That's right. Anyway, bear with me a second. All will be explained. So these are the four possibilities of outputs around a vertex. And the actual matrix element is the corresponding Boltzmann weight, which is one of these A, B, C. So let's see, for example. If the input is two incoming paths, well, these paths have to come out somewhere. So they have to come out both as well. So that means the only possibility is this one. So we already know that there are 3 zeros here, correspond to the fact that you have two paths incoming. There's no way, they have to come out somewhere. And this configuration is all pluses, which I believe was what I called A, the Boltzmann weight A. Similarly, if there's one path coming in, then automatically it can't have two paths coming out or 0 path coming out. And similarly for this one. So we get a bunch of zeros as well here. And the only non-trivial possibilities are these 4 possibilities in the middle. And we might as well do the final one really quickly. If you have 0 path coming in, then it better be that there are 0 path coming out. And therefore, the only non-zero entry is one of these. So we still have, we've already put 1. There are 5 more to go. So this one was called B. This one was called C. This one was called C, B, and A. So the thing you can check is that, OK, I probably erased them. If you remember the 6 local configurations in terms of whatever arrows or whatever, if you redraw them in terms of path, you get exactly this structure. And it's convenient to erase the zeros because to make the structure look simpler. And here's what the L matrix looks like. It has a 1-by-1 block, a 2-by-2 block, and a 1-by-1 block. So these are diagonal blocks. All right? And now the statement is that you can define, so that's the matrix. So, OK, so there's another annoying moment, so is to, make sure we, OK, I guess I'll have to go through this. This is painful. So now I want to express the transfer matrix in terms of the L matrix. So it's just going to be a product of these L matrices, but we have to be really careful on which space they act. So remember that now we have all these vertical lines, which all correspond to a certain C2 tensor L, but there's also the horizontal line we now included as well in the business. So there are really L+1 lines we have to keep track of. So T will be expressed in terms of L by using in a space of dimension 2 to the power L+1. And the way you should think about it is that this is all the vertical edges, 1 by 1. And this is the one horizontal edge going through all of them. Right? So we'll need some notation for expressing this more explicitly. So the space is just C2 tensor L+1. But to be able to distinguish all the copies of C2, we'll give numbers to them. So we'll label, we'll give some labeling to these. So in other words, we'll use, the ambient space will be the C2 tensor L+1, but we'll give numbers to these. So maybe I'll use another color. I don't know if green is visible. So let's try green. OK, so I guess I need to. So let me give the obvious numbering for the vertical edges. I'm going to maybe put it in red. I'm going to number them left to right as 1 to L, obviously. And this one, maybe I'm going to give the index 0 for the horizontal one. And the convention is that OK, I'm totally behind in terms of schedule, am I? Oh, OK, 10 minutes. Well, All right. Could be worse. All right, so the conventionally, let me denote the following. Let me denote the L. So do I use superscripts or subscripts? Yeah, subscripts, yeah. Let me write Lij to be the endomorphism. So here, these are not matrix indices. This is a bit confusing. This is the whole thing is one. So for any ij living in 0 ... L, Lij is a certain linear operator, endomorphism of C2 tensor L plus 1, obtained from L, from the matrix L, by morally, let me say it in words first and then in formula, by making it acting only act only on the ith and jth factors of the tensor product. So very explicitly, tensor product. That means when you write Lij acting on some big tensor product, k, I guess now from 0 to L of sigma k, what it does is that it leaves everybody the same. So the big tensor product is going to be now over k 0 to L sigma prime k, sum over, yeah, tensor product is here. And the rule is that everybody except, so you're going to have a big product of k equals 0 to L, k not equal to ij, of delta sigma I, sorry, delta sigma k, sigma prime k. So this is the Dirac symbol. It means actually all the spins are going to be left the same if they're outside I and j. And only, the only not trivial operation is going to be the L sigma I, sigma j, sigma prime I, sigma prime j, where this is the actual, sorry, the notation is a bit confusing. These are not the same indices. So this is the actual L matrix, 4x4 L matrix, right? So that means it acts on the spins I and j and leaves everybody else intact, right? So that's kind of the schematic representation of, having a vertex involving only lines on I and j. So in the present setting, the only vertices always involve the horizontal line and one of the vertical lines. That means we only really care about L0j, but it's useful for future purposes to have a completely general definition where the idea is the indices means on which space of the tensor product it's acting. So with this language, in other words, you really want to think of this one as being L01, L02, ... L0L. And the statement is then that this, in turn, is again just a trace, basically, because it's, again, we have some cyclicity. So first let me write it explicitly. So it's just summation of rho 1, rho L of, L, well, okay. Yeah, let me just write the final result, because I'm a little bit short on time, so maybe I'll just say it, write the final result. This is literally just this thing. So I have to be careful that products of linear maps go from right to left. So I'm going to write it as L0L, L02, L01. Right, so usually when you take products, yeah, we read products of operators from right to left. So I think this is correct. It doesn't really matter. It would be, but yeah, anyway. So what does it mean? So that means we have to be very careful, what the product means here. It's the product as, I should mention here, what do I mean by product? I mean product in C2, 0, in the 0th copy, 0th factor, well, first, but I'm starting with 0. That means you're only taking the, as usual, pictorially it's easier to understand than in formulas. Pictorially, that means the product means you're only gluing together horizontally and not vertically. And that's why, in other words, it's an usual product horizontally, And it's a tensor product vertically. And tensor product of vertical spaces. That means you're not, of course, concatenating vertically, because we have nothing to concatenate vertically. And that's why when you do this operation, despite the fact that we only have 4x4 matrices, the final result is indeed an operator which acts on L sites, right? So pictorially, it's pretty clear. We've glued all of these together horizontally. All that's left is the vertical arrows coming in and out, and that makes it an operator on C2 tensor L. So that's the, in a nutshell, how you go from successively the partition function to the transfer matrix, and then into its further building blocks, which are the L matrices. And in the remaining 0 minutes, yeah, I'll take 5 more minutes, because otherwise the exercise session is going to be very short. Well, either that or we can, yeah. What do you suggest, Jules? How we should? Yeah, we should continue, right? Because it's not a good place to stop here. Now, in quantum integrable systems, what we try to do, so the philosophy of integrability is not just to, so philosophy of integrability. To diagonalize or to diagonalize T, we're going to embed it into a family of commuting transfer matrices. So diagonalize T, embed it into a family of transfer matrices, with a commuting family of operators. That means we don't want to have a single transfer matrix. Ideally, we'd have typically a one-parameter family at the very least of transfer matrices, because that somehow, this is supposed to be, this is the lesson you learn from kind of classical integrability. When you have many things commuting, that makes things easier. So that motivates the following question. Suppose we have 2 transfer matrices, T and T prime, 6-vertex transfer matrices, but with different Boltzmann weights. And let me call them in the obvious way, with weights A, B, C for T, and A prime, B prime, C prime for, which are always those positive numbers, but distinct numbers for T and T prime. The question is, when does T and T prime, when do T and T prime commute? Right? So that's the question that many people have solved in the past, and particularly Baxter was a great expert in playing this game. And so, of course, that means, in practice, that means T itself is expressed in terms of a certain L operator, 0 L dot 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 0 1. T prime is given in terms of the trace of another L matrix, which only differs from the previous one, that instead of having each time you had an A, B, C, you replace it with A prime, B prime, C prime. And the question is, when do these two things commute? And the trick is the following observation. Assume that there exists an operator which this time is called R, which is also an homomorphism of C2 tensor C2, so also a 4x4 matrix of the same form as L. So that's why it's very tempting to confuse L and R. They're really the same, of the same form, which means it's also a matrix of the form A second, B second, let's say C second, C second, B second, A second. So in other words, it has to have zeros everywhere where the conservation is, the ice rule is broken. Somehow we have the idea in our heads that, we don't really want to do anything that breaks the ice rule. So really, it's just another L matrix, but for some reason we give it a different role and therefore a different name, and we call it R. So suppose we have such a matrix which satisfies a certain identity, which is this crucial, fundamental identity called the RLL relation. And I think this is probably going to be the last thing I have to explain today. And then that can probably work for the exercises. Such that the following identity is satisfied. So let me write it symbolically as So let's see if how did we write the indices? I forget. There was not zeros. Did we use other letters? I forget in the exercises. Is it 1, 2, and 3? Yeah, okay. Such that the following identity, okay, so the labeling may not be entirely consistent, because now I'm labeling starting from 1, not from 0, in and of C2, tensor 3 is satisfied. And first, so I'll write it both. Yeah. Do I have time to do all this? I'm sorry, I'm getting worried that. Yeah, I guess I'll do it. Okay, fine. R1, 2, L1, 3, L prime 2, 3 equals the same in reverse order. Did I put the primes where? Yeah, I guess the same one. Okay, so once again, the convention here is the indices tell you on which spaces they act. So they only act on 2 spaces, but there are 3 of them. So that means you have to choose, 1, 2, 1, 3, or 2, 3. So if you do it pictorially, what does it look like? So as I said, I changed it a little bit. For the purposes of this identity, my labeling is as follows. The horizontal lines are going to be labeled 1 and 2, and there's going to be a vertical line which is labeled 3. And I'm going to let me just first draw it, and then I'll explain. So the vertical line is 3. So L1, 3 prime. I screwed up. The R is supposed to be at the end, which means it's supposed to be on the left, on the right. So remember, you always read identities right to left, and kind of the flow of time is always this way. So yeah, I screwed it up. But by now, no, this is correct. All right. So this is still 1, 2, 3. And this is R. This is R. This is 3. L prime. So first, what does the picture mean? I was forced to add extra little decoration to my vertices because now I've allowed something which I have not allowed before, which is to allow different Boltzmann weights depending on where we are. So basically, I want to mix 2 different models, basically. So I have to say, for this vertex, I'm using the Boltzmann weights of L. For this vertex, I'm using the Boltzmann weights of L prime, using those primes. And for this vertex, I'm using the Boltzmann weights, if you like, of the R matrix, so the entries with a double prime. So that's the first observation. And the second observation is, as I said, if you read this carefully from right to left, first, if you follow the direction of time, first the lines 2 and 3 meet, and that's your L prime 2, 3 vertex. Then the lines 1 and 3 meet, and that's your L1, 3 vertex. And then finally, the 1 and 2 meet. The order is completely fixed by the kind of order in which you read, by the fact that the lines always, you should think of them as flowing from left to right and up, bottom to top. And this is the exact same expression where the only difference is the R matrix is now on the left rather than being on the right, which means in terms of expressions, it's unfortunately exactly the opposite. The R is now on the right because expressions are always read right to left. All right. Do I have time to prove? All right, yes. Then and also I should say R should be invertible. An invertible, because otherwise there's always a trivial solution to these equations, which is R equals 0. So let's say R is an invertible endomorphism which satisfies this, then T and T prime commute. So it gives you a very nice sufficient condition for the commutation of 2 transfer matrices that you have this kind of auxiliary new matrix, which kind of formally looks a bit the same as this R matrix, this L matrix, and which we call R matrix, which allows you to somehow, which satisfies this identity. I think this is probably good enough for the exercise session, so we'll stop here.
Any very quick questions? Okay, yeah, you'll have plenty of time in the exercise session, which starts in half an hour. There are more snacks.
What the fuck?
This
is ridiculous.
Takes longer than
I didn't even get to the actual fun part, which is the RLL relations. Damn it. Yeah.
So the six-vertex model was originally defined for the eyes, right?
Right. Yes.